All right. He's all right. He just his mom just started work there this week, and whew, man, I'm out of breath. The it's all just growing pains. So let's have a look here. Let's go. When we deal with work, here I have a big rock. Very, very difficult to lift this rock there by itself. But we use what's called a lever. Okay? And a lever alleviates some of the force. Not really, but it makes it easier to lift this rock. Because if you were on this side of the log here, you'd be lifting a huge rock. But if you're on this side, depending upon the length of the lever, okay, you're using less force, all right, to lift the rock. Kind of, not really, but I'll show you here. Have a look. There is a catch. This isn't free money, as so to speak. We have to apply our force through a greater distance. So you look, if I want to lift the rock up to here, okay, and let's just call this 3, it's 3 times the force here. Well, left side has got to equal the right side. So therefore now, in order to lift that rock up to this distance here, okay, you've got to move on this side here 3 times the distance. So on this side here, it's 3 force. On this side here, it's 1 force, but it's 3 times the difference. So it all kind of makes sense. And I'll show you what's going to go on here. Okay, so basically what we're saying here is that there must be a connection between force and distance, because we're lifting the rock this much. So either I break my back and I lift it on this side here, or I use a lever and I use 1/3 of the force, but 3 times the distance. Okay, so what do we got here now? The force multiplied by the distance moved is the same for both. And you have a look here. On the left side, or on the right side here, we've got 3 times the distance. There's my input. Okay, you've got the force, and 3 times the distance is equal to 3 times the force, which is what the rock really is, times the distance there of 1 unit that you want to move it. So the force is equal to the force. Input always equals the output. Always, always, always. And here we get into the idea of work. Now, going to work, you know what I mean, it has its societal meanings. But work in physics has a real meaning. Okay? The force that acts times the distance moved in the direction of the force. So what we're talking about here, this is a concept of energy, okay? And it's about moving something, doing something. That's what work is, right? At least that's what my mom always told me. And it's all about the amount carried over a distance. Okay, so every interaction in our universe involves a transfer of energy from one form to another. Energy is a property of a system that allows a system to do work. So work is equal to force times distance. So let's say I have a 5 kilogram box. I apply a force F to it, and it moves a distance d. Well, you've moved the box from here to there over a distance. You've moved it. It's something that's quantifiable. You can see that it's moved, so therefore work has been done. All right? Now, let's say I have a 2,000 kilogram box, and I'm applying a force. Okay, I'm sweating. I just pulled a muscle, one of my rhomboids. Biology, you guys should know what a rhomboid is. And but the box didn't move. Well, I've applied a force to this box, so there is a force, but the distance was 0. So anything times the number 0 goes to 0. If the box didn't move, there ain't no work. Work is not a vector quantity as no direction is associated with it. Okay? Work can either be positive or negative. Whenever an object moves and there is a force acting on it, work is done. Move the box this way, move it this way. Work is positive when the force and the motion are in the same direction, negative when they are in opposite directions, and non-existent when they are not in the same plane. Let's read that again. Work is positive when the force and the motion are in the same direction. So I'm pushing the box this way. The force is being applied this way. The box moves this way. That work is positive. Negative when they are in opposite directions. So let's say I'm pushing the box this way, but the force of friction, okay, that's underneath on the floor, is pushing this way. All right, negative force. And so you just you add them as you would normal negative numbers, right? And non-existent when there isn't any. If there's no force being applied, that's it. What do we got here? Work. To do positive work, okay, in the physical sense or the physics sense, when you lift the crate. Okay, I think that should say crate, actually. Interesting. Good. There we go. You do no work in the physical sense when you carry the crate. So you see, you're doing weight when you lift it from the floor to, as this person has right here, right? So the boxes were on the floor. Work was done to the boxes by lifting them up. Remember, I don't know if you guys, I'm sure you guys have heard of potential energy. We're going to get into potential and kinetic energy there today. But you see, the boxes moved up. He's now carrying them. Work has been done. But when you walk across the room and carry the boxes to another place, you know, there's no work done because the boxes aren't doing anything. All right, you are carrying them. So there's no force, nothing being done to the boxes there, no work. And you do negative work when you set the crates down. Good little example here of positive work, no work, and negative work. All right. This is a good one right here. Welcome to the joule. Excuse me. The joule is the unit of measure of work and energy. Okay. I guess the old school imperial system, they use the calorie, which we're more familiar with here, because in Canada we have this strange mix of, pounds and kilograms, and some stores use kg, some use pounds. We measure ourselves in pounds and inches, and so it's very odd here in Canada as far as, for a person coming here, are we using the SI unit of measure, or are we using imperial? Here we use both. But 1 joule actually means 1 Newton meter. And what that means is 1 joule of work is done when a force of 1 Newton is exerted over a distance of 1 meter. All right, that's the definition. I think that's in your formula sheet. And have a look here. These are the type of questions there that we're looking at. Because of friction, a constant force of 100 newtons is needed to uniformly slide a box across the floor. If the box moves 3 meters, how much work is being done? Well, work is equal to force times distance. I give you the force, 100 newtons. You give you the distance, 3 meters. Is equal to 300 Newton meters, which is actually equal to 300 joules. Okay. Let's have a look at this one. Here is same formula, but watch and see. Example, let's say that the barrel had a mass of 30 kg and that the height of the dock is 1.2 meters. How much work would you do when lifting the barrel? Well, you have a look. And I put this there in my formula sheet. Okay. And you'll see here that work is equal to force times distance, which is also equal to mass times gravity times distance. And this is for this one right here, MGD, is mainly for lifting things up. Questions like that. Okay? So if you look at the example here, let's say the barrel has a mass of 30 kg and the height of the dock is 1.2 meters. So work is equal to mass, gravity, distance. Mass, gravity, 9.8 meters per second squared and 1.2 meters. And there you go, 353 joules to lift that guy up. Okay. Again, another question, the same thing. Give you newtons, give you meters. There you go. Work is equal to that. Calculate the work done in lifting a 500 Newton barbell 2.2 meters above the floor. There you go. Plug and play. Now, this one though, thank you guys for coming. I really want you guys to see this. We had, and this question here will definitely apply to chemistry. It's one of the things I'm going to talk to my peeps about there in my chemistry class there on Thursday, where, and instead of just telling you this here, I'm going to show you guys what's going to go on. So, taking a test, you never know what question's coming next, right? So you kind of have to reset yourself. What is this question asking for? And what information am I given? What is my strategy? What is my roadmap? How am I going to get to that answer? And you have a look here. How much work is being done to accelerate a 100 kilogram car from 0 to 27 meters per second in 10 seconds? We know a force of 2,700 newtons will be applied. Okay, so I've got, here are my knowns. This is what I pulled out of the question, because I try and get away from language as much as possible. Okay, I'm just dealing with numbers here. So I got a mass of 100 kg. I got the change in velocity, which is from 0 to 27. So you remember V2 minus V1. Okay, if we need it. So our change in velocity is 27 meters per second. I got change in time. If we need this, who knows? Maybe we won't need it. I don't know. I do know. We know that a force of 2,700 newtons will be applied. And what are we looking for? What did I just hear? Oh, no, I think they're in a good mood. There's two of them down there. And they're all by themselves. All right, so here we go. And we're looking for work. Now, okay. So we're looking for work. Work is equal to FD, or it can be equal to MGD. Okay. All right. But work is equal to FD. Okay, so do I have a force? Okay, I have a force of 2,700 newtons. But wait a second, I don't have distance. How am I going to figure this out? We don't have distance. Okay, what related formula has distance in it? So this is where now you go back to your formula sheet. And you see, this is where you want to be. This is what the question is asking. But I don't have distance. So then you got to find a formula that has distance and backtrack. So, okay, I need this formula here to find distance, so I can plug it into this formula to find work. Okay, so distance is equal to half acceleration t squared. Okay, I have time, 10 seconds, but acceleration, I don't have acceleration. So that, oh, no, they're fighting. And so here's your formula there for acceleration. Okay, And so what I'm asking you to do for this question is you got to find the work done. But in order to find that, I've given you the information. You're going to have to go back all the way to acceleration. You see here, I needed distance before. Okay, distance equal to acceleration. I don't have acceleration, so then therefore find the formula there for acceleration. And you'll see acceleration is equal to v2 minus v1, which we have, 27, and time is 10 seconds. So there's my acceleration, okay, which is 2.7. And then you sub that into distance, and you get distance is equal to 135 meters.
Daddy, Holly got a marker.
Okay. Well, see what you can do about it, okay? Can you see if you can get it?
No, we can't. Holly's too scared and Holly's too fast.
All right. Well, see what you can do. Keep me posted.
No.
Hey,
I'm
talking with my students. Get out of here.
Please get it.
All right. Get out of here. You're going to get it.
In 1 minute, you need to come downstairs right away and get that marker.
All right. Apologies, but what are you going to do? I'm sorry, but I'm not. And you see what's going on here. Okay? I'm looking for this answer, but I only gave you stuff for this. So you got to plug in here, sub it in here, find your distance, sub it in here, and you get your answer. Welcome to the way this stuff works. There's the quiz that'll go out there today. You'll see one of the questions. I'm not going to tell you which one, but you'll probably see it when you see it. This is exactly it. I think you've got to use at least 2 formulas, maybe 3.
Daddy, Mine said I need to do it again.
Okay, Shire, I'm talking. Okay.
But Daddy said
you can't be. You gotta go. I love you, but I'll see you.
okay, and get that marker really well. Okay.
All right, I promise.
In 2 minutes, okay.
All right, jeez. Welcome. This video will probably go.
1 minute, okay. 1 minute.
Bye.
Bye.
All right. So, please be aware that anything is fair game now. And you see this formula right here, acceleration, it's not on this, okay? Which means you may need your other formula sheet, okay? Which is posted, which you can print off, it's all there, okay? So just be careful. Anything's fair game. Using a question there to sub in for another question, it's all in there, okay? Getting into energy. Now there are many different kinds of energy. There's geothermal, there's chemical, electrical, nuclear, gravitational. You know, even along the lines of energy associated there with heat and light and sound and all these kinds of things, right? So, but energy is measured in joules. Okay, and what's a joule? Just going back here, where'd that go? And I just wanted to show you right here. 1 joule is equal to 1 Newton meter. Okay, the force exerted over. So, energy, the measure of a system's capacity to do work, that which is transferred when work is done. So, in order for work to be done, there has to be some type of transference of energy in some way. And you look at, I had a peanut butter and banana sandwich there this morning. Absolutely one of the best sandwiches going, by the way. Try it, peanut butter and banana. And you see my body is currently breaking it down, all right? And I'm retrieving energy from it, okay? Chemical energy. And then I can feel the friction, the heat. And I've just made heat. You've just transferred energy from one form to another. And please know that you cannot destroy. Energy is transferred, but us as human beings, we cannot create nor destroy anything. Okay? Energy just gets transferred into a different shape or form. Welcome to another formula. Again, these are all triangle formulas. Okay? Maybe if you guys want all the triangle formulas there that are in here, All right. Hello, what's going on? Like, there's a triangle formula. This one here is a triangle formula. If I get enough requests, maybe I'll do it. But power is equal to work divided by time. Okay? And work is in joules, right? We just did that one wherever it was, right here. Work is equal to force times distance. All right? And then you have power is equal to work divided by time. So power is in watts. And 1 watt is a joule per second. Okay? And so 1 watt of power is used to do 1 joule of work in 1 second. And an example, we've seen watts there before. A 60 watt light bulb uses 60 joules of energy per second. That's how that one works. So 60 watts, 60 joules per second. So power is equal to work divided by time. And again, these are just plugging and playing. A ton of bricks has a weight of 8,900 newtons. Needs to be loaded from the ground to the bed of a truck 1.2 meters high. Okay? 2 ways to do this. You could lift it by hand, one at a time, which will take an hour. Or the bricks can be loaded in 10 seconds with a forklift. And the next slide here, we're going to go over the numbers of what's going on here. But again, let's go over my scenario. Here I have a ton of bricks, whack load of bricks. And I need to lift them onto the back of this truck, which is 1.2 meters high. Okay? I can do it one at a time by hand. It'll take an hour. But I can use a forklift to do it in 10 seconds. A couple of things here I want you to take notice of. The work, if you're doing it by hand or if you're doing it by forklift, will be the same. Okay? Do that again. It's the same amount of work to take all the bricks and put them onto the back of the truck one by one as it is by doing it in 10 seconds with a forklift. The work done is equal to the work done. But where things are going to be different is in the power, which is watts per second. All right? One's only going to take 10 seconds. Another one there is going to take an hour, which is what, 3,600 seconds. Okay? Have a look at the math here. I've just laid it out here for you. So this one here, very, very, very important. The work done equals the work done. Now let's have a look at the power output there by the forklift. Okay, you see there, power is equal to work divided by time. Well, power is equal to 10,680 joules, which is what we said it was here, divided by 10 seconds. Okay, which means that the forklift is operating their power at 1,068 watts. But have a look at one at a time. Again, the same work in joules, but now we've got 3,600 seconds because it took an hour, right? 1, 2, 3. And look at my wattage. My wattage is only 2.97 watts. Okay? So, what does all this mean? Let's keep on trucking. So, just before I move on to the next slide, have a look at this example, all right? Because you've got 2 different scenarios that end up in the same, all the bricks will end up in the back of the truck, by forklift or by hand. The work done is the same, but power is a measure of work done in a second. So how much work is being done in a second? Well, here, in a second, you're burning over 1,000 watts. In a second, you're only burning 3 watts. Okay? So this is a cheaper way of doing it, but it's longer. Okay, but ultimately the same amount of work gets done. Let's have a look here. Test yourself. If two equal mass sacks are lifted equal distance in equal times, how does the power for each sack compare? Well, if they got two equal masses and they're both lifted at the same time and they're both lifted the same distance, if they're basically the same, then everything is going to be the same regarding their power. But look at number 2 here. If one of the sacks mentioned above is lifted in half the time, so you remember, go back to your forklift. Okay, if now you're able to do the same job in half the time, the power has got to be doubled. It's all got to be balanced in some way or another. Even think back to the lever there with the, I think it was a lady there in a rock. Okay? You can't cheat physics. Either you're going to lift this rock, I don't know, what was that, a meter? Either you're going to lift that rock to a meter, or you're going to lift a third of the rock 3 times as far. So everything always balances out. So here, if my sack, if I lift it in half the time, I need to double the power. Okay? Calculate the power expended when a 20 Newton force pushes a cart 3.5 meters in 0.5 seconds. So calculate the power. Okay, power is watts, work divided by time. Do I have work? I got newtons and I got meters. No, I don't. I don't have work. So then I got to go back and go back to my formula. Whatever you don't have, whatever you need for the formula that the question is asking you, if you don't have work, then jump back. Just like that other jump back and find a formula for work that fits. And you see here, I gave you the information there for work. You solve it. Work is equal to 70 joules. Now, 70 joules divided by 0.5 seconds is equal to 140 watts. Okay, there I just put a little green little reminder here that again, I gave you information there. I want you to find power, but I gave you the information for work. You're going to have to solve for this one and then plug in. Welcome to it. That's what it's all about now. Okay, kind of bringing, because physics, chemistry, biology, all these things, they're not separate and distinct. They're all one. It's just somebody at some point in time said, no, this is biology, this is physics, oh, and chemistry's over here. No, they don't touch, they're distinct. Doesn't work like that. Everything is an amalgamation of everything. Okay, so know that one formula there, you may need to pull in another formula in order to get the job done. What do we got here? Calculate the power expended when a 20 Newton barbell is lifted 2.2 meters in 2 seconds. Okay. So here again, calculate the power. I didn't give you power. I gave you the information there for work. And then you plug that in and away you go. Okay. Energy. Anything that has energy because of its motion or because of its position is said to have energy. Okay? Just the whole analogy there, I think I was talking about there last week in my chem, is that like only at absolute zero do molecules stop moving. And it's kind of a theoretical thing because we don't really know, because the only place that absolute zero exists is out in space in between, I don't know, Mars and Jupiter, where there's nothing. And I can't even measure it, because if I go out there in my spacecraft, get my spacesuit on with my thermometer, and I go out floating into space, it's not showing me absolute zero because I have brought atoms. I brought my thermometer, which has heat and all this kind of stuff with it. So, you know, this whole idea of absolute zero It's a theoretical thing that, but we can kind of guess that it's there, and the mathematics works. And but when we get into the two types of energy there that we're going to kind of talk about there today, there's kinetic energy and potential energy. Oh, and I tell you, you better know these ones. All right. Kinetic energy, which I should have talked about this there in chemistry as well. It's the energy associated with motion and friction, these kinds of things, right? So you have ice molecules, water molecules that are below zero, so they're ice. They're not free to move, but what they do is they vibrate. Okay, because they have heat. Even though it's minus 20, they got heat. All right? And then if you add heat, you put a lighter or put this ice onto the burner of the stove, what happens is they start vibrating even more, and then once you start to get close to zero, you get what's called, I call it a popcorn effect. You get these molecules of water that break off from the ice, and now they're free to, well, kind of free, because water is kind of free, and this continues until all the ice has been broken into liquid water. So you got all the water moving around, and it has more energy than it did as ice. And if I keep adding heat to this pot of water, what happens is these guys here start moving around so fast, and at 100 degrees Celsius, you will start to get more popcorn, where these molecules of water jump and become gas. All right, so kinetic energy, energy associated with motion. All right, and we use the symbol Ke, kinetic energy. Potential energy just means energy associated with a position, an object's position or orientation. Basically, it's storing energy. I'm lifting this pen up and up and up. Right now, it has zero kinetic energy because it's not moving. All right, but it has a lot of potential energy. And I'm just trying to think of some. What can I do here? Okay, I have this. This will do. All right. So here, this is my table, and I've just put my pen on there. All right. So it's not really moving. It's not anything. It has zero potential energy. It doesn't have any stored energy. It's just sitting there. But now, if I raise it up, it has potential energy. How do I know? All right. This is what we're talking about. You have done something to this, and now it has potential energy. All right. So we'll get more into this right here. Potential energy is energy associated with a system's position or orientation. So kinetic energy is the energy due to the motion of an object. And here's the formula. Kinetic energy is equal to half mass times the velocity squared. Another formula, I'm going to give you numbers, you plug and play. What is the kinetic energy of a 1,000 kilogram car when it is traveling at 27 meters per second? There you go. It has a kinetic energy of 364,500 joules. That's it. So that's the energy associated with motion. Okay. The energy of a moving object is proportional to the square of its speed. Okay, so you increase the speed, there's a square beside that V. So the more you increase the speed, that thing will jump huge when you square it. So if you increase the velocity of an object, you are greatly increasing its kinetic energy because of this square right here. Okay, with the V in the square. Okay. Therefore, if one car is moving twice as fast as an identical car, two cars, two Honda Civics, exactly the same, I got one car is moving twice as fast as another. So I got one car moving 50 kilometers an hour and another car, exactly the same car, same mass, moving at 100 kilometers an hour. Would you believe that the faster car now has 4 times the kinetic energy? Because if the one car is traveling twice as fast, what's 2 squared? 4. So this thing now has 4 times the kinetic energy. And it will take 4 times the work to stop it with your brakes. That's why when people are driving, try not to tap your brakes all the time, because that's where you're really taking them down, is when you're traveling fast. Even if you have a clutch, if you have a standard car, you can actually shift down and don't use your brakes as much. But the faster you go, the faster your brakes will go. Potential energy. Okay, this is stored energy. Potential energy is the energy an object has due to its position. And we're going to focus on gravity, right? Raising things up. All right. Since work is done against the force of gravity, is technically called gravitational potential energy. As you like. Okay. And the formula for this one here, potential energy is equal to mgd. Mass times gravity times distance. Should kind of look familiar. Boy, I kind of miss my son. I hope they're all right. Potential energy is a relative quantity because positions can be measured relative to different levels. I like this right here. We have 2 scenarios. Have a look here. Make it make sense to you. You've got it right here. Here I've got a table, and it's a meter high. Okay. And number 1 here, when a 3 kilogram brick is lifted 0.5 meters above a table, its potential energy relative to the table. Now, let's go back to week 1. You remember, I want to say Spider-Man in a ham sandwich. You remember that one there? I forget who was on the truck that was on the boat. But, you had different perspectives of where your speed was. Like if you were sitting on the battleship, okay, the speed of the truck would look different because now you are the same speed as the battleship, right? Things would look different if you were looking on the ground or it's all about perspective, right? Well, have a look here. When a 3 kilogram brick is lifted a half meter above a table, its potential energy relative to the table is. So you can kind of just ignore all this. So you've just, basically the top of your table is the ground. That's how you want to that's what this is kind of implying here. So I raised the 3 kilogram brick a half meter off the top of the table. So you see here, potential energy, find your formula, mgd, 3 kg, 9.8 meters per second squared. That's from gravity. And your distance here is only a half meter. So your potential energy, according to the tabletop, is 14.7 joules. But have a look now. What is the potential energy of the brick in relation to the floor? Well, you look here, the floor is 1.5 meters away. So that'll be the only difference there to our equation right here. And you'll see here that the potential energy, according to the floor for that brick, is 3 times as much. All right, it's 44.1 joules. Okay, so good little example. Be careful. You might see relative to the, which may have to alter your thinking a bit when you're trying to measure potential energy. Am I asking it for it relative to the ground, or am I asking it relative to the top of the table, kind of a thing? Just be careful. Good little one there to note. Test yourself. Okay, and here we're all dealing with kinetic energy. A moving car has kinetic energy if it speeds up so that it is going 4 times as fast as it was before. You remember that whole velocity? So if we now we're going from 20 kilometers an hour to 80 kilometers an hour, we have now just increased our kinetic energy by 16. Good little question. I like it. Huge understanding there. Okay? You got to pull in all these different resources there just to answer this question. Okay? All because of that square right there. Calculate the kinetic energy of a 3 kilogram block of ice moving at 4 meters per second. So I'm asking you for kinetic energy. I think there's only one formula there for kinetic energy. So you just go to find your formula. Kinetic energy is equal to a half mv squared. Plug and play. And again, same thing here. Calculate the kinetic energy of the same block moving at twice the speed. Well, here we were traveling at 4 meters per second, 8 meters per second, away you go. Are we good? Potential energy. Some of these are good, so let's have a look here. And I put these in here, and I'll show you how to use these. I'll use these. I'm going to put them up here and see how things go. A car is raised on a certain distance on a service station lift in the garage. You know, when your car goes on the lift there and they look at underneath it, right? And it now, because it's been lifted, it now has potential energy, right? If it were raised twice as high, how much potential energy would it have? So my distance, what is that going to do to my answer for potential energy? So you see there, we raised it 5 meters. If we raise it 10 meters now, basically you've doubled all of this. So if you double the distance, you've doubled the potential energy. Okay? 2 cars are raised to the same elevation above the floor in an auto shop. 2 cars, same. If one car has twice the mass as the other, compare their potential energies. So if they're both at the same distance, but one car is double the mass of this one, well, let's have a look here. If I double mass, what is that going to do to everything here? I will double the potential energy. Okay, so basically what these 2 questions show, if I double the distance of the car being lifted up, I've now doubled the potential energy. If I double the mass of an object, I've doubled the potential energy. Okay, so calculate the potential energy of a 20 kg block of ice lifted a vertical distance of 2 meters. Plug and play. Okay. Energy cannot be created or destroyed. Of course it can't. But it can be transferred from one form to another. The amount of energy in a system always, always, always remains constant. Okay? And the whole idea, if we raise something, we're increasing its potential energy. Is it moving? No. If I let it... So when potential energy goes up, kinetic energy goes down. Kinetic energy goes up, potential energy goes down. And you think about it. If a football is going up, all right, there's eventually going to be a point. You see, it's going up, 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 up. It's increasing its potential energy to when it comes to the top. You're throwing a football in the air, right? And it goes like this. At the top here, it's going to have its maximum potential energy because that's as much energy as this ball can store in this particular arc. The top, that's where it's got its maximum potential energy. But then as this thing comes down, now you are increasing its kinetic energy. Why? Because it's moving. Well, I'll show you a couple of these right here. And a drop in potential energy will result in an increase in kinetic energy. And have a look here. A brick at rest on a table. So you just have a brick on a table. It's sitting there. It has a high potential energy. It's not moving. All right. So it has 0 kinetic. But if you kind of slide it off, right? So the brick is sliding off, okay? As it's coming down here, the potential energy decreases, and as it's falling, the kinetic energy increases. I got, if it's not clear, if it's clear as mud, it will be. I got some good stuff coming up. Whenever objects collide, now you guys will remember your momentum. You remember, I think, what was it? The silly putty. There's an example on the quiz there of a bullet hitting a block of wood. Now this all has to do with your momentum, right? M1. You guys remember that? M1v1 is equal to M2v2. All right. But there are 2 kinds of collisions, and I want to show you guys these here. Okay. We've got elastic collisions and inelastic. Now, elastics are bouncy. Inelastic are not bouncy. Write that one down. That's a good one, just so you can tell the difference. You have a look here. Elastic conditions, where the kinetic energy from before will equal the kinetic energy after. Momentum before will equal the momentum after. An inelastic collision means that these guys are not equal. Something's going on here. Energy is being changed or altered, and it's going into a different form. So therefore now the same energy is still there, but the same energy there to do things is not. We'll show you this. What do we got right here? Please have a look at these. What this guy does is he takes a really, really, really bouncy ball and another ball, basically the same mass, and the other one there is not bouncy. He takes a ball like this and another ball like this and drops them both. This ball here bounces. This ball here just goes thud. And he rolls them down and hits a block of wood. And it's really, really good little video on the differences there between elastic and inelastic. Okay? One of the things there that I don't want you to forget about is I'll update you guys there before the week's over on, your test should be multiple choice, but there will be some matching definitions because this is a new language, and you can count on the very fact that I'll ask you there the difference between elastic and inelastic collisions. It's important stuff. So have a look at these videos. I want to show you this. And this kind of just shows you what's going on here. Like, here are 3 examples of an elastic collision. Okay, so you got one ball here. Okay, you got 5 joules of kinetic energy moving in this way here. This one here is 0. It ain't moving. And what happens is when this guy here knocks this guy, there's a transfer of kinetic energy. And you'll see what goes on there. The first ball that was moving ain't moving anymore. The second ball that wasn't moving is got the 5 joules of energy coursing through its veins, and now it's moving. Okay, another example. Here I got 5 joules going this way, 5 joules going this way. Now, think elastic. Elastic collisions, think bouncy, bouncy balls. Moving all over the place, bouncing. What's going to happen here? They're going to meet, they're going to transfer, and they're going to go back the way they came. So this energy here was transferred here, and now this ball is going in this direction, and the other ball there transferred its energy. So, okay, and let's just go on. I'll keep going. And I don't know if you guys can see that or not there at the bottom. Here I got 10 joules and 5 joules, and they're both going in the same direction. Transfer. And you'll see there that the 10 joules was kicked forward and the 5 joules was kicked back. Okay, so elastic collisions, there's a complete transfer of energy. Okay, 1 + 1 = 2. Everything adds up. Not so for inelastic. You have a look here. Here I've got 5 joules moving this way, 0 joules moving not moving at all. And you'll see what's gone on here. Oops, sorry, if I can. And you'll see here what's going on is that the numbers don't add up. All right, we lost a joule of energy, probably as heat. Okay, so something went on here. This is what we call an inelastic collision. Okay. Yeah, we're almost done. A couple slides and that's it. Good. That takes us to an hour. That's exactly where I want it to be. Test yourself. What will the kinetic energy of a hammer be when it undergoes a 10 joule decrease in potential energy? So the conservation of energy says that energy can neither be created nor destroyed, but only transformed. So therefore, a 10 joule decrease in potential energy means a 10 joule increase in kinetic energy. So what will the kinetic energy of a hammer when it undergoes a decrease in potential energy? Remember, potential and kinetic work like this. So if this one goes down 10 joule, the other one has got to go up. And it works the same like this. Write that down somewhere. That's easy marks, but easy to forget or make a mistake on it, okay? So potential energy and kinetic energy work opposites. If you increase 10 joules on one side, you got to decrease it on the other. Have a look at this one. An apple hanging from a limb of a tree has potential energy because of its height. If the apple falls, what becomes of this energy? Just before it hits the ground and when it hits the ground. So an apple's hanging, okay, and it falls. We want to know what's going on with the apple just before it hits the ground and once it hits the ground. And if you think about it, just before it hits the ground, it's moving its fastest. It has maximum. Just before the apple hits the ground, just about all of the potential energy has been converted to kinetic. Okay? When it hits the ground, the potential energy will be 0, and the kinetic energy will be equal to what the potential energy was prior to its falling. So it's all about maximums here. Okay? The apple's hanging in the tree. It's got maximum potential. It's falling through the air, just about to hit the ground. Okay, its potential energy is pretty low. Its kinetic energy, it's been moving so fast, is at its maximum there. And that's what happens there. And then when it hits the ground, all right, kinetic, it's all about transferring. And if you think of potential energy is stored energy, kinetic energy is moving energy. They happen opposite to each other. Okay, these pair of scissors here are sitting on my tabletop. They're not moving. Okay, I raised them up. Okay, it's got potential energy. Doesn't have any kinetic. There it had kinetic. All of its potential is now gone. All right, so what do we got here? Railroad car A rolls at a certain speed and makes an elastic collision with car B that is at rest. So we have car A and car B, and they make an elastic collision. After the collision, car A is at rest. How does the speed of car B compare with the initial speed of A? And this whole question here is just this one right here. Okay, you got car A, which is coming in at some speed. You got car B, which has 0. It's just sitting there. Okay, car A hits car B. Car A ain't moving anymore. Car B has taken all the energy there that car A had. So that one right there is exactly that question. Okay. And because an elastic collision occurs, momentum mv is conserved. Therefore, the velocity after the collision will equal the velocity before the collision. Car B will move off with the same velocity that car A had prior. Number 4, last question. If the cars from the previous question are of equal mass and they stick together after colliding, how does their speed compare after the collision with the speed of the car A prior? And the answer is the speed after the collision will be half. Because if you use that formula there, if they're all the same mass, okay, then now the mass is doubled. All right, and that's your momentum. All right, so this is what we've got here. Next week is test 2 on weeks 4, 5, and 6 material only. Your quiz will open up there in, actually I could probably open it up now. What do I care? Give you guys more time. So I'll open up the quiz right now. There's a paper copy that you can print off and just tootle away there all week, and I love it. And then there's an answer sheet input portal there that you would just upload your answers to as normal. So I think that is due next Tuesday at noon, okay? And I was going to make it there till midnight, but it's only till noon because we got a lot of things going on there, okay? And I want that quiz finished up by noon by the time next week's class is, okay? Other than that, I hope your labs are going well. You guys are doing great, and if you guys have anything there for me, just kick around after. And I don't know where my son is, cutie patootie. But that's all I got there for today. Go on, get out of here. I'll open up the test there, or I'll open up the quiz as soon as I can. But you guys have a great day, and I'll post this there to YouTube. If you all got any questions, kick around. Other than that, thank you. You guys are good. You as well, Mallory. Thanks, Austin. And anyone who needs to stay, stay. All right. I'm just going to stop recording now. And